巴黎生活的气氛一下 Hello everyone, welcome back to UNGG 1310. Sorry about the short delay because of the network problem on my computer. Alright, so let me first enable the cloud recording. Okay, so the cloud recording is already enabled. Now let me share my PowerPoint with you. Okay. Alright, so last week we stopped on page 46, right? If I remember correctly. 46. Okay. So we stopped on talking about the Maxwell equations in the one-dimensional case. Okay, so let us continue. So on page 47, we're going to see the two equations that we derived in the previous slide. So the first one is the partial E over partial X equal to minus partial B over partial T. So this one is the very magnetic field induce an electric field. So the other one is minus partial B over partial X equal to mu naught epsilon naught partial E over partial T. So this is a very electric field induce a magnetic field. Okay, so then starting from this set of equations, we first differentiate with respect to X for the left equation. So this becomes a second derivative. And then, so here this becomes a double derivative with both variables of X and T. And on the right hand side, we do differentiate with respect to T. So the left hand side becomes minus partial T bracket partial B over partial X. And right hand side is the second derivative of E with respect to T. Okay. So it is natural that these two terms are equal to each other because the partial differentials are commutative. So that means the two variables can exchange their positions. All right, so this basically they are equal to each other. So we establish a relationship between the second derivative of E with respect to X and the second derivative of E with respect to T. So that is the equation for traveling electromagnetic waves, this one. All right, so based on that equation, you know that this kind of a wave equation has solutions of sine or cosine forms, right? Sine or cosine forms. So we then express the solutions as a function of cosine. So here the variables omega is equal to 2 pi times f is the angular frequency, and k is the propagation constant, which is defined as 2 pi over lambda. All right, then we just substitute the expressions into those equations. All right. So on the left-hand side, if you do the derivative, cosine becomes minus sine. At the same time, you have this minus k. And on the right-hand side, again, becomes minus sine. And based on the chance rule, you have the prefactor minus omega. So this sine cancelled out. So you have E max over B max equal to omega over k. By definition, omega over k is equal to c, the speed of the wave, the electromagnetic wave. On the right-hand side, similarly, this sine and sine cancel out. So based on this equation, you eventually have E max over B max equal to k over mu naught epsilon naught omega. Yes? So you finally get E max over B max equal to 1 over mu naught epsilon naught C. Alright, so that means C is equal to 1 over mu naught epsilon naught C. So that means C square is equal to mu naught epsilon naught. So you get the expression for C. C equal to 1 over square root mu naught epsilon naught. Alright, so far so good. I guess the derivation on this page is quite straightforward. You just follow the math. Do this step by step. Okay. Alright, move on to the next page. So just now we derived that the expression for the speed of traveling electromagnetic waves expressed as this. So when Maxwell first formulated this result, the two constants, so one is the permeability constant and the other is permittivity constant. The two constants had already been fairly accurately measured. So he just did a very simple calculation and found out the wave speed should be 2.998 times 10 to the 8th power meter per second. So at that time, people have already measured the speed of light, and it's quite close to that value. So he immediately realized that light might be a form of electromagnetic wave. Well, at that time, that was just conjecture. So that stimulated many experimentalists to verify the existence of electromagnetic waves. And one of the most prominent experimentalists is Henry Hertz. In 1887, Henry Hertz designed experiment and demonstrated the propagation and wave properties of electromagnetic waves. So here, let us watch this video so that you can have a more vivid picture of what Henry Hertz did about 150 years ago. All right, here we go.
In the modern world, we humans are completely surrounded by electromagnetic radiation. Have you ever thought of the physics behind these traveling electromagnetic waves? The great scientist, Heinrich Hertz, was the first man to transmit and detect electromagnetic waves. In his famous experiment, a high-voltage current was applied to the two ends of two metal wires, which generated a spark in the gap between them. This spark resulted in the radiation of electromagnetic waves. Those electromagnetic waves traveled through the air and created a spark in a metal coil located over a meter away. If you had placed an LED in that gap, the bulb would have glowed. This was a clear case of electromagnetic wave propagation and detection. However, before Hertz...
Okay, so this is a long video, and the rest of the video is not relevant to the Henry Hertz experiment. All right, let us come back to the PowerPoint slide. So even Hertz demonstrated the existence and verified the presence of electromagnetic waves. At that time, he didn't realize the importance of electromagnetic waves. He commented that, well, my experiment only proved that existence of electromagnetic waves. It would have no application at all. But obviously, after 150 years, you know that Hertz was wrong. So nowadays, you probably cannot live without electromagnetic waves. Nowadays, electromagnetic waves are everywhere. So in the next section 3.4, I'm going to talk about more details of electromagnetic waves. So nowadays, people already know that light is just a part of electromagnetic spectrum. Electromagnetic waves covers a huge orders of magnitude, starting from the lowest frequency, like the long waves, then to radio wave, then to infrared, and then comes to the visible spectrum. So only the electromagnetic waves within the visible spectrum can be seen by human being. And then beyond that, if we keep going toward the higher frequency, then we enter the region of ultraviolet, the next X-rays, and next one is gamma rays. Okay, no matter what frequency is, the speed of the electromagnetic wave is always c. As I mentioned, 2.998 times 10 to the 8th meter per second, and most of the time it's just approximate as 3. That is 30,000 kilometers per second. So 30,000 or 300,000. Sorry, 300,000. 300,000 kilometers per second. All right. So all of them share the same speed, but they have different frequency. So that means the lambda, the wavelength of the electromagnetic waves, can have very long to very short. Okay, so more specifically, the electromagnetic spectrum is divided into these types. First, the radio waves. The radio waves are the lowest frequency electromagnetic waves that we find useful. And radio and television broadcasts are in the range of 1 megahertz to 1 gigahertz. So 10 to the 6th power hertz is 1 megahertz. 10 to the 9th power hertz is 1 gigahertz. So then next is the microwave. Nowadays, microwaves have been everywhere. They are used for cooking. I guess all of you have microwave ovens. It's very convenient. You just put it into the oven and set the power switch on the power, then you can easily heat up your food, right? Very convenient. And for communication, you know that the telecom band for communication is around several gigahertz. That is in the microwave regime. So microwave frequency are from 10 to 9th power hertz to 10 to 12. So 10 to 12 hertz is 1 terahertz. With wavelengths from 1 meter to 30 centimeters. So next one is infrared waves. So why are they called infrared waves? This is because the infrared wave, so if you go back to the previous page, the infrared regime is on the lower frequency side of the visible spectrum. And you know that the lowest frequency for the visible spectrum, the color for the lowest frequency in the visible spectrum is red. So below red, then people gave it a name of infrared, which means its frequency is below that of red. So infrared waves are felt as heat by humans. Also, remote controls operate using infrared radiation. The frequency are from 1 terahertz to 430 terahertz. 430 terahertz, yes. The next one, visible light. Visible light actually has a fairly narrow frequency range from 4.3 times 10 to the 14th hertz. So that means 430 terahertz to 750 terahertz. Which corresponds to the violet light. All right, so going to the even higher frequency than the violet, that is ultraviolet. And you probably can get the meaning from this prefix ultra. So ultra means beyond, higher and beyond. So ultraviolet light starts from frequency just above those of visible light, from 750 terahertz to 10 to the 17th power hertz. These rays cause tanning, burning, and skin cancer. Some insects have ultra capabilities to see the ultraviolet, and some flowers have special markings that are only visible under ultraviolet light. Okay, so moving on to the next. Next one would be X-ray. So X-rays have higher frequency from 10 to 17th to 10 to the 20th hertz. They are used for medical imaging. So nowadays, when you have your bones fractured, you go to the hospital and the doctors, in order to examine your situation, then the first thing would to ask you to get an X-ray image. And next one will be the gamma rays. Gamma rays have the highest frequency of all, above 10 to 20th power hertz. These rays are extremely energetic and are produced from nuclear reactions. They can destroy living cells and can also be used for destroy cancer cells and sterilize foods. Okay? So far, so good. Any questions? Okay, let's move on. So nowadays, electromagnetic waves are everywhere. People use them for telecommunication, for transmitting information through the undersea cables, by using optical fibers, and also radios, GPS for you to positioning your location, and X-rays to get image of your organs, and last one, lightings. So all of this cannot be possible without electromagnetic waves. Okay, so talking about electromagnetic waves. First, electromagnetic waves are transverse waves. That means the direction of wave propagation is perpendicular to the direction in which the field components oscillate. So what does it mean? Let's look at the example shown at the bottom left. So here, this is the purple curve shows the varying electric field intensity, and the blue curve shows the varying magnetic field intensity. So they are perpendicular to each other. So say this is X, so this is Y, and this is Z. So the propagation direction is along the Z direction. And the electromagnetic fields oscillate in the plane of X and Y, XY plane. Okay? Electric field and magnetic field are always orthogonal to each other. And in vacuum, electromagnetic waves always propagate at the speed of light, 1 over square root epsilon naught mu naught. Okay? So the first example, that will be plane waves. And plane waves will be the simplest form of electromagnetic waves. So for the electric field and magnetic field, it can be expressed in terms of this kind of a cosine function with amplitude E, H, and this called a phasor. And inside, it represents the phase. So here you can tell that if you want to find out which direction that this wave propagates, then you just need to set this phase to constant. Set this phase to constant. Then as t increases, you can find z also increases. So that means if you want to track a certain point on that electromagnetic wave, then you need to move in the positive z direction. So that means the wave is propagating along the positive z direction. Okay, so the fields have constant amplitudes, which do not vary in the plane. That's the xy plane. The plane propagates in direction, for example, x direction, that is perpendicular to the fields, with angular frequency omega and phase shift kz. Kz is called phase shift, while k is propagation constant. All right, so you may want to ask, what is k defined? K is equal to n times k naught. And k naught is the wave number inside the vacuum. Wave number inside the vacuum is defined as 2 pi over lambda. Lambda is wavelength. And n is the refractive index of the medium. So basically you can tell that let me say a few more words about this. So because k is equal to nk naught, and k is equal to 2 pi over lambda inside the medium, and k naught is n2 pi, nk naught is n2 pi divided by lambda. This lambda is inside the vacuum. So what conclusion do you get? The wavelength in the medium is equal to the wavelength in the vacuum divided by n. with n being the refractive index of that medium. Yes? So that means once this wave enters in a medium with refractive index of the medium being n, then its wavelength is reduced by a factor of n. Okay? So far so good? All right. So next example of electromagnetic waves would be spherical wave. Spherical wave. So in our everyday life, actually, we can find many such examples. For example, if you have a light bulb, and once you stand far away from the light bulb, this light bulb can be treated as a point light source. As a result, the electric field, or in other words, optical field of the light that emitted by this light bulb would follow this spherical wave function. Okay, so again, inside the bracket, this is the phase. As I mentioned, if you want to track some specific point along that wave, then you need to set this to be constant. You set this to be constant. So that means as t increases, your r has to increase. In this way, you know that the wave is radiating along the radial direction. R increases along the radial direction. Okay? In the meantime, its amplitude falls. Its amplitude falls as R increases. And it's inversely proportional to R. Why is this? Because of energy conservation. Or because of power conservation. The power has to be conserved on the surface of that sphere. So as R increases, the larger distance away from the light source, then the lower light intensity. Okay? So I guess these are quite clear, straightforward. Huh? Any questions? Okay. So next, we're going to talk about the polarization of electromagnetic waves. So as I mentioned before, there are two components. One is electrical field, and the other is magnetic field. They are always orthogonal to each other. They're always orthogonal to each other. So in this community, people define polarization as the direction of oscillation, the oscillation direction of the electric field component. Electric field component. Remember, now let me remind you, although we define polarization with respect to the electrical field component, that does not mean that electromagnetic wave contains only electric field. Electromagnetic waves always contain both electrical and magnetic field. And as I mentioned, they are always perpendicular or orthogonal to each other. Always orthogonal to each other. So once you define the oscillation direction of electric field, then you know that magnetic field is perpendicular to that. As shown in the two examples at the bottom. So this polarization direction is vertical because the electric field is oscillating vertical along the z direction. And on the right hand side, the polarization direction is making angle of 60 degrees with respect to the y direction, because E oscillates along that direction. Okay, in order for you to get the deeper understanding of that, we have animation to show how a linearly polarized light wave look like. Hold on for a second. Let me bring up the video. Let me share the screen with you. Screen. Right here. Okay, here we go. All right. Okay, so let's come back to the PowerPoint slides. So moving on to the next. So just now you watched the animation for linearly polarized and cyclically polarized light. So what do they mean? Consider the superposition of two plane waves of frequency omega traveling in the z direction with propagation constant k. The electric field can be represented in the general form. So as I mentioned, this is the phase, which tells you that the wave propagates along the positive z direction. In the meantime, this is the amplitude, the vector amplitude. So this vector contains three components, x direction, y direction, and z direction. Now since this wave propagates along the z direction, so this must be zero. This must be zero because EM wave is transverse wave. So the z component must be zero. So there are only x and y components. All right. So then we can plot the x and y component in this xy plane. And without loss of generality, we can define Ex to be real number. We can define Ex to be a real number, and Ey to have an additional phase with respect to the X component. So delta phi is a relative phase difference of the X and Y components. Okay. Well, you may argue, why can we set Ex to be a real number? Well, it does not matter. If it is not a real number, say J phi 0, if it's not a real number, it does not matter. That becomes this, right? J phi x. And more generally, J phi y. You can always take that constant, the constant phase out of the bracket. And here delta phi becomes phi y minus phi x. Only the relative phase difference matters. The common phase will not matter. You probably still want to ask why the common factor will not matter. Because usually when we talk about the light, we are looking at its intensity. Intensity is the modulus or the absolute value squared. So in this case, the common factor in front of the bracket becomes 1. It does not matter. Okay? Alright, so once you agree with me on this, then it'll be easier to understand the following definitions. So for linear polarization, we have the two components, the Ex and Ey, moving in phase. So in this case, delta phi is equal to plus or minus 2m times pi, m being an integer. And the polarization angle depends on the relative value of Ex and Ey. All right, so here is a right triangle, right? This is Ey, this is Ex. So based on a trigonometric relationship, we can find out tangent theta is equal to Ey over Ex. All right, any questions? Quite clear, huh? All right, so this is the linear polarization for in-phase situation. In the second scenario, they are out of phase. So the delta phi is equal to plus minus 2 pi plus 1 pi, with m being the integer. Okay, so in this case, then the Ex and Ey components are out of phase because, as you can tell, when Ex is negative, Ey is positive. And when Ex is positive, then Ey is negative. So they always have opposite sign. They always have opposite signs. So here tangent theta is equal to minus Ey over Ex. Okay? Next, delta phi is equal to minus pi over 2 plus or minus 2n pi. This is because Ej half of pi is equal to minus j. This gives you a 90-degree phase difference between the X and Y component. So as a result, in the meantime, you also need to have the x and y components to have the same magnitude. X, y components have the same magnitude. So in this case, you're going to find out that the electric field, the vector, rotates as it propagates. All right. So by this IEEE convention, you fix a point in the space and look away from the source in direction of propagation. And then you follow temporal revolution. You're going to find out the electric field actually is moving clockwise. So in this way, you can tell that this clockwise rotation can form a right-hand relationship with the propagation direction. So it's called right-hand polarization. So it's called right-hand polarization. Okay, any questions? Next, if delta phi is equal to pi over 2 plus or minus 2m pi, then you can tell that J delta phi will become J, right? So that means still the x and y component have a phase difference of 90 degrees. But this time, the field vector is rotating along the counterclockwise direction. So again, the wave propagation direction is still positive z, pointing into the page. But the field vector is rotating in the clockwise direction. So in this way, if you use your thumb to point to the direction of propagation and the four fingers curving around the direction of the field vector rotation, then you find out you have to use your left hand rather than right hand. So in this case, it's called left hand polarization. Any questions? Well, just now we mentioned two types of polarizations. So the first one is linear polarization. You need to have delta phi equal to either 2m pi or 2m plus 1 pi to have linear polarization. For circular polarization, you need two conditions. The first, you need to have x and y component of the E field with the same magnitude. Second requirement is you need to have a phase difference of these two components to be half of pi. It can be minus half of pi for right-hand polarization and plus half of pi to be a left-hand polarization. Circularly polarized state. Well, if these kind of conditions cannot be satisfied, then what is the general case? So either E field have different x and y components, or you have a phase difference between the x, y components to be any other values. You're going to have this general form that relates Ex and Ey component. And this is called elliptic polarization. Okay, so it's already 3:18. Let us have a 10-minute break. If you have questions, please feel free to leave a question in the chat box. Yeah, I can already see some of you have questions. All EM waves above 10 to the 20th is gamma? Yes, that's correct. What's RE bracket? RE bracket, that's a function represent taking the real part of the function inside the bracket. So yes. Another student asked about the data of midterm. We don't have midterm. We only have final exam. Okay. Yeah, let's have a break. We'll come back around 3:28. let us come back to the PowerPoint slide. Okay, so just now we talked about linear polarization. And there is another type of polarized light, which is called unpolarized. So unpolarized light actually have polarization in all the directions. So to represent that kind of unpolarized light, we use this symbol to cross with double-headed arrow. Okay, so next we still talk about linear polarizers. So how to generate light of linear polarization? A polarizer is an optical field that passes light of specific polarization and blocks wave of other polarizations. And a polarizer converts a beam of light of undefined or mixed polarization into a beam of well-defined polarization. Okay, so basically there are two types of linear polarizers. So the first one is absorptive polarizers. Well, this kind of polarizers absorbs all the unwanted polarization states. So as shown here. So if you have this kind of polarization sheet, once you send an unpolarized light through this polarization sheet, it will block all the other polarized state and only allow the vertically polarized light pass through. Why vertically polarized light? Because the polarizing angle of that polarizing sheet is along the vertical direction. All right, the second type is beam splitting polarizers. So in this case, the unpolarized beam is split into two beams with orthogonal polarization states. So for example, so here you have a mixed state, and after propagating this beam splitting polarizer, it's split into two parts. One is the O wave and the other is E wave. And O wave has one polarization state, and the E wave has the orthogonal polarization state. Okay, so a polarizer will transmit the component of light in the polarizing direction. So for example, so here you have a polarizer. Its polarization direction is along this line. Makes an angle of theta. Makes an angle of theta with respect to the vertical direction. Then, if you send the light with the intensity I0 with vertical polarization through this polarizer, then the transmitted light will have intensity reduced to I0 times cosine theta square. And the reason for this additional factor, cosine theta square, is because I is equal to E square. E is the electric field. And because the electric field has to be projected to the polarization direction. And this becomes E cosine theta. So after square, it becomes E square cosine square theta. So that's where this additional cosine theta square comes from. All right. So, okay, I've already showed you how you get this additional cosine theta square, right? This is because this E field has to be projected to the Y axis, giving EY. And I is EY square. Okay. Well, if you send an unpolarized incident beam through a polarizer, then the transmitted beam will have an intensity of half of I0. This is because if you do the average of cosine theta, that becomes 1/2. If you do the average of cosine theta, that becomes 1/2. Okay, so combining the two effects that we mentioned in the previous slides, if you have a combination of a polarizer and analyzer, if you have polarizer and analyzer, then the final intensity will become half I naught times cosine theta squared. Why is that? Basically, you can decompose this into two steps. First, once a polarized incident beam passes through the first polarizer, then you have its intensity drop by half. That is what we have here at the end of the last slide. So this beam, now you have a defined polarization state along the vertical axis. And this vertical axis makes an angle of theta with respect to the transmission axis of the analyzer. So that gives you an additional cosine theta squared. Okay? Is that clear? All right. Well, you might want to ask how this kind of strange polarization states are generated. So they are generated by different process. Unpolarized light can be partially or completely polarized by scattering from atoms or molecules. For example, if a gentleman standing at top of a mountain see unpolarized light from the rising sun, then the ladies lying on a chair gonna see polarized light of the sunlight by the scattering from the sky or from the cloud. So different process generate different light of different polarizations. And in another process, a gentleman standing on the beach will see the reflected light of sunlight, linear polarized. And actually, we're going to talk about this phenomenon with details in the subsequent topic, where we introduce the so-called Brewster angle. Okay, so far so good. All right, so next we'll talk about the intensity of electromagnetic waves. The intensity, because electromagnetic waves carry energy and they propagate through space, they can transfer energy to objects placed in their path. And the rate of flow of energy of electromagnetic waves can be described with the vector S. And S is defined as E cross multiply H. So as you can tell, if this is E and this is H, then E cross multiply H gives you the direction of S. Exactly the same as the direction of propagation. Okay, so the average intensity of plane wave is given by this or this. And we're going to provide the proof on the next page. So the magnitude of the Poynting vector represents the rate at which energy flows through a unit surface area, perpendicular to the direction of wave propagation. So the SI unit of the Poynting vector is the unit of E multiplied the unit of H. So unit of E is volt per meter, and unit of H is ampere per meter. So as a result, you know that V times A is watt, right? Volt times ampere is watt. So this W. And for the denominator, this Meter and meter gives you meter square. Okay, so that's watts per meter square. Watt per meter square. All right. Let me see. I can see a question popping up. Where is it? Let me see the question from Mark YU. If I'm polarized through a vertical polarization and horizontal polarization, will I equal to 0 or I equal to 1/4? I will be equal to vertical and horizontal. I will equal to 0. Yeah, let me confirm the answer. The answer will be I equal to 0, because after vertical polarizer, then the light is polarized only along the vertical direction, and the vertically polarized light cannot pass through a horizontal polarizer because they have 90 degrees. So cosine 90 degree is equal to 0. Okay. Well, let me continue on the intensity of electromagnetic waves. So for a plain electromagnetic wave, E cross B equal to EB, because E and B are always perpendicular to each other. So then S is equal to E times B over mu naught, because this is H, right? This is H. Since E over B is equal to C, oh, this you have to keep that in mind, because we derived that in the previous slide. E over B equal to C. Where is it? We derived that at the beginning of this lecture here on this page, page 48. On page 48, E over B is equal to C. The ratio between the electric field and magnetic field is the speed of light. Come back to the intensity of electromagnetic wave. Okay, come to here. E over B is equal to C. So substitute this relationship into here. Then we have two expressions. S equal to E squared over mu naught C, or equal to B squared times C over mu naught. Okay, for sinusoidal plain electromagnetic wave, the intensity is the time average of S, because the time average of this cosine square function is 1/2. So as a result, you just add 1/2 to the previous expression. So you have this and this. At the same time, the U total. What's U total? U total is the energy density, the instantaneous energy density. So this energy density times the velocity of the wave propagation is equal to this I, is equal to the intensity. So the instantaneous energy density should be equal to I over C, right? I over C. So UE is half of mu naught E square, and mu B is B square over 2 mu naught. And because of this relationship, yeah, we can tell that this relationship comes back again and again. E over B equal to C. So you can express the U total as mu naught E square or B square over mu naught. Emission naught E square or B square over mu naught. And for this average energy density will be half of emission naught E max square or B max square over 2 mu naught. Okay? Alright, so we have introduced too many formulas, huh? So let us look at an example so that you have a better understanding. So estimate the amplitude of E and B fields of the light that's incident on this page because of visible light coming from your desk lamp. 60 watts. Treat the bulb as a point source of electromagnetic radiation that is 5% efficient at converting electric energy into visible light. So that is 3 watts. Distance from light bulb to page is about 0.3 meter. Alright, from energy conservation, you have I equal to P over 4 pi R squared, right? The P is the total emitted power, the total emitted power by this light. So that is 3 watts. And 4 pi R squared is the surface area of a sphere with a radius of R. And this I, what is I? I is expressed here. I expressed here. So you have expression of I here. Either you can use this formula or use this formula. Alright, so here we use E max square over 2 mu naught C. Alright, then we substitute all these numbers into the formula. Then we can get expression for E max. And finally, we get 45 volts per meter. And for B max, remember, B is equal to E over C. So it's 1.5 times 10 to the negative 7 Tesla. And U total will be B max square over 2 mu naught. So substitute all these numbers, and finally we get 9 times 10 to the negative 9 joule per cube meter. Alright, so far so good. Okay, so after talking about the intensity, let us look at momentum and radiation pressure. So electromagnetic waves transport a linear momentum as well as energy. And this momentum is absorbed by some surface. Pressure is exerted on the surface. Assuming normal incidence, Maxwell showed that if the surface absorbs all the incident energy, U in this scheme, U in this time, then the total momentum P transport to the surface has a magnitude U over C. So this is for complete absorption. So what complete absorption means? So that means there is no reflection at all. There's no reflection, so completely absorbed. The pressure P, still P, but we use a capital letter. The pressure P exerted on the surface is defined as a force per unit area. Right? So P is equal to F over A. And what is F? F is the force. Force is equal to dP over dt. This is what? This is the impulse theorem, right? From the Newtonian mechanics. Substitute F equal to dP over dt into here. And P is equal to U over C. So finally you have 1 over C times du over dt divided by A. So F is the force and A is the area. Wait. So if you look at this factor more closely, you find out what's this. This is the rate at which energy is arriving at the surface per unit area. So what's that? That's exactly the magnitude of the Poynting vector. So that is I, the intensity. Okay, so then we derive that the radiation pressure exerted on the perfectly absorbing surface is P equal to I over C. P equal to I over C. Pay attention, the uppercase and lowercase. So this p, so small p, is represent momentum, and this big P, the uppercase big P, represent pressure. So small p is equal to U over C, and big P is equal to I over C. Okay, so far so good. All right, so we have talked about the case for the perfect absorption. So what is the case for perfect reflection? Well, for the case of perfect reflection, the momentum transferred to the surface by the coming light is P equal to U over C. At the same time, transferred by the reflected light is still U over C, right? So in this case, you have to add a factor of 2 in front of U over C for complete reflection. Likewise, we can also derive that the big P, the pressure, should also be revised as QI over C for the case of complete reflection. Well, in the most general case, you would neither have a perfectly reflecting surface or perfectly absorbing surface. So usually you have the momentum between 1U over C and 2U over C. And also the radiation pressure is between 1I over C and 2I over C. Okay. Well, actually, some scientists have proposed that we can use the radiation of sunlight to act as a booster for our as a booster for the solar travel or space travel. Although this radiation pressure is very small, but you can tell that it is always pushing this kind of equipment. So as the time goes, this can still accumulate to a very large velocity. Okay, so next we look at an example of momentum and radiation pressure. The sun delivers about 1,000 watts per meter square of energy to Earth's surface via electromagnetic radiation. So first calculate the total power that is incident on the roof of dimension 8 by 20 meter. Second, determine radiation pressure and the radiation force exerted on the roof, assuming the roof is covered by a perfect absorber. Okay, so part 1 is power is equal to I times A, right? I is already given, and A is the area of the roof, 8 times 20. So this one is easy. Second, pressure is assuming it's perfect absorber. So you know that P is equal to I over C. And I is already given, and C, speed of light. So that gives you 3.33. And force is P times A. So since we already have the pressure, then just substitute into here and multiply by the area of the roof. So finally you get 5.33 times 10 to the negative 4th Newton. So you can tell that this is very small. This value is very small. This force is about 533 micronewton. Actually, this force is very small. Okay. Well, any questions? We've talked about the many formulas regarding electromagnetic waves: intensity, momentum, and radiation pressure. So far, so good. Do you have any questions? Okay, no question. Then I'm going to move on to talk about some relationship between the Rev index, permittivity, and permeability constants. So we have already seen how the Rev index n relates to the speed of light in the medium. So this Vp is equal to c over n. So that means in the medium with Rev index of n, is the speed of electromagnetic waves is going to be reduced by a factor of n. Additionally, we also prove that the traveling wave solution of Maxwell's equation, C, is expressed as 1 over square root mu naught times epsilon naught. So now we come to a relationship between n and the relative parameters epsilon r and mu r. Just for information, this epsilon r is the relative permeability and is an alternative symbol for kappa, where we introduced for the dielectric constant of the material. Okay. So in vacuum, we have the coefficients epsilon equal to epsilon naught, mu equal to mu naught, Vp equal to c. And the wave speed is 1 over square root mu naught epsilon naught. Therefore, Vp is equal to 1 over square root epsilon mu equal to c. In other words, mu r equals to 1, epsilon r equals to 1. However, in a medium, the coefficients are epsilon equal to epsilon naught mu epsilon r, mu equal to mu naught mu r, and Vp equal to c over n. So in this case, the wave speed becomes Vp equal to 1 over square root epsilon mu, and then you express epsilon as epsilon naught epsilon r and mu equal to mu naught mu r. Okay, and then by using this relationship, so then it's expressed as c over square root epsilon r mu r, which means that this one should be equal to this one. So n is equal to square root epsilon r mu r. In most of cases, for dielectrics, mu r is equal to 1. So n is equal to square root of epsilon r. Please pay attention that this n and epsilon r are frequency dependent. They are frequency dependent. What frequency? The frequency of the electromagnetic waves. If the frequency is different, then this n or epsilon r can be very different. And actually we have a name for that. That's called dispersion. Dispersion. For example, once you send a beam of white light through a prism, you have different angles for different color of light, right? Different color of light. So that means this n is different. This n is different for different color of light. Different color of light means that different frequency of electromagnetic waves. So that's a clear example that n actually depends on the frequency of electromagnetic waves. Okay. All right. Next, we're going to talk about the properties of wave propagation once it transmits from one medium to another medium. For example, you have medium 1 and medium 2. Medium 1 has Rel index of n1, medium 2 has Rel index of n2. Then what is the reflection of the electric field, and what's transmission of electric field? So here we define the reflection coefficient as the reflected electric field divided by the incident electric field. And for the transmission, we use transmitted electric field defined by the incident electric field. They can be expressed as a simple formula, including N1 and N2. And they are derived from the boundary conditions. So I can quickly derive them for you. Before that, let me review the boundary conditions I introduced it to you previously. Let's review the boundary conditions. Where is it? Boundary conditions here. On page 8 in this topic, the boundary conditions for electromagnetic waves are what? The perpendicular component of D continuous. Parallel component of E continuous. Perpendicular component of B continuous. And parallel component of H continuous. Alright, to derive that relationship, we just need these two conditions. So in that case, there's no surface current. So that satisfies this continuity requirement for the parallel component of H. Okay, so let us come back to page 82. So we want to derive the relationship between ER and EI, and also ET and EI. Let me bring the whiteboard. Okay, so we have two media, medium 1 and medium 2. Okay, so in medium 1, we have an expression for the parallel component of E. E parallel is equal to EI plus ER. Because we have two fields in medium 1, two electric fields in medium 1. And in medium 2, we have only one electric field, right? We only have ET. No problem? In medium 1, H field, we have HI minus HR. Pay attention, minus. And H for in medium 2 is equal to HT. All right, as I mentioned, these two have to be equal to each other. They have to be equal to each other. On the other hand, we also need to express H in terms of E. We also need to express H in terms of E. So because E is equal to B epsilon. B is equal to mu h. Right? Is equal to mu over epsilon times h. Okay. So that means h is equal to epsilon r epsilon 0 mu r mu 0 e equal to n 0 mu 0. Right? So here basically we assuming mu r is equal to 1 and epsilon r is equal to n. So this is assumed in most of cases for dielectrics. You have mu r equal to 1 and n equal to square root of epsilon r. Okay, so once you have this relationship, you can substitute h for e. You can substitute h for e. And the other two are constant, you can tell. This is constant. Okay, so you have the two equations. Back to the left hand side. You have two equations. EI plus ER equal to ET. The first one. Second one, N1 EI minus N1 ER equal to N2 ET. Alright, so far so good. Alright, then we divide EI on both hand side. Divide EI on both hand side. So this becomes 1 plus R equal to T. The second one, N1 minus N1 R equal to N2 T. Okay? Then you can simply solve for R equal to N1 minus N2 divided by N1 plus N2. And T equal to 2N1 divided by N1 plus N2. Okay? Any questions? No question. Okay, then I'm going to close this whiteboard and return to the PowerPoint slide. Alright, so just now I've shown you how we can derive the expression for R and T based on in terms of N1 and N2. So next let us look at several specific examples. For example, N2 greater than N1. So for example, N2 is equal to 4 and N1 is equal to 2. So if you just substitute those numbers into these expressions, very easy, right? You can simply get R equal to minus 0.33 and T equal to 0.66. Wait. If you have sharp eyes, you find that there is an additional minus sign here. So what does minus mean? Okay, so the minus sign just means that the reflection coefficient or the refracted waves undergoes a pi phase shift at the boundary. A pi phase shift at the boundary. And I will show you what that means in the next slide by looking at this animation. Alright, so this is the incoming wave. Okay, the reflect wave, you see? The reflect wave is inverted, right? You can tell that this black reflected wave, the black curve, the reflect wave is inverted with respect to the incoming wave. So because of that, there is an additional minus sign for the reflection coefficient. Okay, well, let us move on. So in the next example, we have N2 smaller than N1. So for example, we give N1 over equal to 4 and N2 equal to 2. Still, we substitute those numbers into these two formulas, and we find that R is equal to 0.33. So now you relax. This time there's no minus sign. But then you find another problem. T is greater than 1. So what does that mean? T greater than 1. So T is transmission coefficient. So does that mean you have even stronger transmitted wave compared to the incident wave? Before I answer your questions, let us look at this animation. Actually, the answer is yes and no. Yes, you do have a transmitted wave with a larger amplitude than the incoming wave, but that does not mean that the energy is not conserved. That does not mean that energy is not conserved. So here it is. Even you have T greater than 1, there's no violation of energy conservation. This is because we are considering the field amplitude, not the field intensity. We're considering field amplitude, not field intensity. So remember, we defined this Poynting vector. Because Poynting vector defines the rate of energy transport, right? The Poynting vector defines the rate of energy transport. Then it is this quantity, S, that should be conserved at the interface. Therefore, we have this relationship. And by cancel this E on both hand side, so we have this relationship, 1 minus R squared equal to N2 over N1 T squared. We have this relationship. It is not 1 minus R equal to T. No, not this. Okay? All right. So we actually give a new name for these two terms. So this one, we call it reflectance rather than reflection coefficient. Call this reflectance. And this one, big T, we call it transmittance of the interface. So the small r is reflection coefficient, small t is transmission coefficient, but the big R is reflectance, and big T is the transmittance. All right, so with that definition, then we can easily express the reflectance and transmittance in terms of N1 and N2. So R is equal to small r squared, then simply is N1 minus N2 divided by N1 plus N2, then square. And big T is N2 over N1 times small t squared. So eventually you get 4N1 times N2 divided by N1 plus N2 bracket square. So in this case, you can verify yourself. Now R plus big T is equal to equal to 1, right? So now in this case, you can tell that now this is equal to 1. The energy is indeed conserved. Okay? Alright, so since already 4:15, we do not have time to cover the rest of the lecture. So we're going to stop here for today. Let me make an announcement. If the Secretary of the Faculty of Engineering did it correctly, you should have already received the email reminding you to fill out an online teaching evaluation form. So we appreciate that you can spend a few minutes to provide feedback for the instructors. So far, I believe you have already received the forms for both Professor Zi and myself. I'm Professor Sun. So Professor Zi taught you on the topic in the first 4 weeks, and I'm currently teaching you on magnetostatics and also electromagnetic waves. And the next week will be another instructor, Professor Zhao, to continue teach this course. So at this moment, you can give the evaluation form for both Professor Zi and myself. So we really appreciate that you can spend several minutes to fill out the evaluation forms and to give us some feedback. Thank you so much for your attention. Okay, so if you still have questions in the course content, excuse me, please feel free to leave the message in the chat box. Otherwise, you are free to leave. Thank you very much.